A. Scarred yellow bar arrives at a refinery under seal. It may contain 60 to 90% gold. After refining, it may emerge as a bar stamped 999.9. Yet, even that level of purity cannot answer the harder question. Where did this gold come from? Once processing begins, its old shape will vanish in the furnace. The laboratory can prove how much gold survives, but only evidence can decide whether the new bar is merely pure or clean enough to trust. And by clean, I do not mean shiny. Purity describes the proportion of gold inside the finished metal. Clean describes something chemistry alone cannot measure, whether its origin and journey through the supply chain can be sufficiently documented and accepted. The refinery must therefore deliver 3 separate verdicts. Is the gold pure? Is the finished bar authentic? And after the original object has been melted out of existence, can its past still be verified? Later, one metal with nearly the same density as gold will reveal why even the correct weight cannot settle the second verdict. The rough bar on the receiving table is called doré. It is an intermediate product created from gold recovered at a mine. Alongside gold, it may contain silver, copper, and smaller amounts of other material. Its color reveals almost nothing about the precise proportions. The refinery records the seal, weight, identifying marks, supplier, and shipment documents. But before the laboratory answers what lies inside, follow this bar backward into the darkness before it had a face. Gold rarely waits underground in the form people imagine. Enormous nuggets exist, but most modern mines pursue gold distributed through rock in particles too small to see. A ton of apparently ordinary ore may contain only a few grams depending on the deposit. The process begins with core drilling. Cylinders of rock are extracted from beneath the surface, logged, and analyzed. Geologists combine thousands of results into a 3-dimensional model showing the location, shape, depth, and grade of the deposit. Model separates valuable ore from rock that may look almost identical, but cost more to process than the gold inside it. If the deposit lies close enough to the surface, the mine may become an open pit. Soil and barren rock are removed to expose the ore body. Drill rigs create carefully spaced holes, and explosives fracture sections of rock in controlled sequences. Excavators load the broken material into haul trucks capable of carrying hundreds of tons, yet a truck filled to its limit may hold only a small amount of gold hidden within an overwhelming mass of rock. That is the first great imbalance in this story. Gold bars are compact, because the mine has already discarded almost everything that once surrounded them. When valuable ore lies too deep for an open pit, the operation may move underground. Shafts, ramps, tunnels, ventilation, drainage, and ground support systems must be built before production can advance safely. Drilling and blasting still break the ore, but now the work takes place inside confined passages under geological pressure. Sensors watch for movement, gas, water, and changes in air quality. Remote equipment can enter places considered too dangerous for a driver. None of this means gold has been made. The mine has merely reached the rock that contains it. Ore from the pit or underground workings is delivered to a processing plant. Primary crushers break large pieces into smaller fragments. Secondary crushers reduce them further. Grinding mills then pulverize the material until gold-bearing particles become accessible to the next recovery stage. Inside a rotating mill, steel grinding media rise and fall through the ore. Every impact creates new fractures and exposes more surface. The machine is not simply making dust. It is opening pathways to gold that chemicals and gravity could never reach inside solid rock. The recovery method depends on the mineralogy. Where enough free gold exists, gravity systems can exploit its high density. In many operations, however, the ground ore enters a cyanidation circuit. Under controlled chemical conditions, gold forms a soluble complex with cyanide. The metal can then be separated from much of the material that once trapped it. Cyanide is highly toxic, so industrial facilities require engineered containment, monitoring, water management, treatment systems, and trained operators. It can recover gold from low-grade ore with remarkable efficiency, but that efficiency carries a responsibility extending far beyond the processing tank. The gold-bearing solution may pass through activated carbon, precipitation, or another recovery system. Gold is then concentrated and recovered, often through electrowinning or related stages. What emerges is not automatically a 999.9 bar. It may be a sludge, precipitate, or cathode product containing gold alongside other material. Mine site electrowinning recovers gold from a process solution. It should not be confused with the high-purity electrorefining performed later at a specialist refinery. The recovered material is dried and heated with carefully selected fluxes. These help unwanted components separate into slag, while the dense, precious metal-rich phase settles below. Molten metal is poured into a rough mold. When it cools, it becomes dor. It finally has the shape of a gold bar. Shape is about to be destroyed. Large industrial mines are only one part of the global supply chain. Across Africa, Asia, and Latin America, millions of people depend on artisanal and small-scale gold mining. These operations are not identical. Some are legal cooperatives working towards safer practices. Others operate informally or illegally. For many communities, small-scale mining is one of the few available sources of income. Its most dangerous methods can place miners, families, and entire ecosystems at risk. Mercury is used at some sites because it forms an amalgam with gold. Fine particles that would be difficult to collect mechanically can bind with the mercury, creating a mass that can be separated from the surrounding material. The amalgam is then heated. Mercury escapes as vapor, leaving a gold-rich residue behind. The process looks simple enough to perform with basic equipment. Its true cost may remain invisible for decades. Mercury vapor can damage the nervous, digestive, and immune systems. Mercury released into soil and water can travel through an ecosystem, be transformed into more dangerous compounds, and accumulate in the food chain. The United Nations Environment Program estimates that artisanal and small-scale gold mining produces roughly 12 to 15% of the world's gold, while representing the largest source of mercury releases to the environment. This danger is not confined to distant or unregulated mining regions. During the California gold rush, mercury amalgamation helped recover gold from immense quantities of sediment. More than a century later, mercury remains in parts of the landscape. Flooding and erosion can disturb contaminated material and carry it farther downstream. The miners left. The rush ended. The gold entered coins, jewelry, and private fortunes. Part of the mercury stayed behind. Get gives the word clean its first dark contradiction. A refinery may remove mercury from the metal. It cannot pull mercury back out of every river, forest, or human body previously exposed to it. By the time gold reaches the refinery, its chemical impurities can still be treated. What occurred at the mine is much harder to undo. Back at the refinery, the dor is still waiting for its first verdict. The incoming bar is weighed. Its documents, seal, markings, supplier, and lot number are checked. Yet taking a random shaving from one corner may not reveal the true composition of the whole bar. Dor is an alloy, and an imperfectly mixed alloy may contain local variations. Surface contamination can also distort a careless test. When large amounts of money depend on a tiny sample, that sample must represent the entire lot. The refinery therefore melts the incoming material under controlled conditions. Once the metal has been sufficiently homogenized, a representative sample is drawn from the melt and sent to the laboratory. This small sample may determine how much fine gold is credited to the supplier, how much silver can be recovered, and which refining route the material should follow. A tiny analytical difference multiplied across a large shipment can represent significant value. Fire assay remains an important reference method. A precisely weighed sample is combined with selected fluxes and heated. Gold and silver are collected and separated from much of the surrounding material. Further treatment allows the laboratory to determine how much gold the sample contains. Instrumental techniques can supplement the process depending on the material and purpose of the analysis. But the goal remains the same: convert an uncertain yellow object into a measurable inventory of metals. The first verdict arrives. The bar is real gold-bearing material, but it is not pure gold. The assay identifies how much gold, silver, copper, and other material entered the refinery. The result establishes the theoretical amount of fine gold that should emerge after processing. Before the refining begins, tell me where you're watching from and whether you believe gold can ever be called truly clean. The refinery now has a scoreboard. It knows what came in. From this moment forward, every residue, solution, anode, cathode, and finished bar must help explain where that gold went. The dor returns to heat and loses its shape for the second time. Depending on the refinery and required product, the gold may pass through processes such as Miller chlorination, Wohlwill electrorefining, or a combination of stages. In the Miller process, chlorine gas is introduced into molten impure gold under carefully controlled conditions. Silver and many base metals react more readily than gold, forming chlorides that can be separated from the gold-rich melt. The process can produce gold around 99.5% pure or better, depending on the feed and operating conditions, is high enough for some important wholesale standards. But if the intended product requires even greater purity, another stage may follow. The Wohlwill process takes the metal apart through electricity. Impure gold is formed into anodes and suspended in an electrolyte containing gold chloride and hydrochloric acid. Thin sheets or starting surfaces of high-purity gold serve as cathodes. When electrical current passes through the system, gold from the anode enters the electrolyte and deposits at the cathode in a much purer form. Silver does not simply travel with it under the same conditions. Other precious metals and impurities behave differently and can collect in residues or separate processing streams. What began as a rough bar is now distributed across an industrial system. Gold at the cathode, silver compounds, anode residues, process solutions, and recoverable byproducts. The metal has not simply been cleaned. It has been dismantled according to chemistry and rebuilt. This is also where refining becomes an accounting problem. Gold is too valuable to treat an unexplained loss as ordinary waste. Residues are tested, solutions are monitored. Filters, crucibles, dust, and processing equipment can all contain recoverable precious metal. Even the material swept from controlled refinery areas may require treatment because microscopic losses accumulate. When the electro-refining stage is complete, high-purity gold is removed, washed, and prepared for melting. Another sample confirms whether the intended fineness has been reached. The familiar numbers now appear: 995, 999, or 999. These describe millisimal fineness, the number of parts of gold per thousand parts of material by mass. A bar marked 999. 9 claims that 999, 9 parts out of every 1,000 are gold. That number is not marketing poetry. It is a laboratory statement. It is also not the only legitimate standard. Many small investment bars are sold at 999. 9. While London Good Delivery gold bars require a minimum fineness of 995. A genuine 995 bar is not fake or unfinished, simply because another product carries an extra 9. The required purity depends on the product, refinery, customer, and market. If the second assay falls below specification, the material cannot be wished into compliance. It returns for additional refining. If gold remains in a residue or solution, recovery continues until the metal balance can be properly explained. At last, the first verdict is complete. The gold is pure enough for its intended product. It returns to a furnace and is heated beyond gold's melting point of approximately 1064 degrees Celsius. The actual operating temperature can be higher, so the metal remains fluid during transfer and pouring. For a cast bar, a prepared mold waits below. Workers in heat-resistant clothing control the crucible or pouring system as dense molten gold flows into the cavity. The metal glows orange, folds across the mold, and begins losing heat almost immediately, but casting introduces its own failure points. As gold solidifies, it contracts. The surface may develop ripples, depressions, or characteristic cooling patterns. Some are normal features of a cast bar. Others may indicate porosity, inclusions, irregular filling, or a defect that affects acceptance. A cast bar is not expected to resemble a perfectly machined block. Its surface records the physical behavior of molten metal during cooling. Minted bars follow a more controlled shaping route. Refined gold may first be cast into a larger form and rolled into strip. Blanks are cut, weighed, adjusted, annealed, cleaned, and struck with dies to create sharp designs and uniform surfaces. Minted bars often look more polished and carry a higher manufacturing premium. Does not mean a rougher cast bar contains less gold. The new bar cools. It is removed from the mold, cleaned, and placed under bright inspection lights. The assay says it is pure. Its surface shines. Its rectangular form looks complete. And this is where the story reverses. Chemistry has made the gold more uniform and valuable. At the same time, the furnace has erased almost every visible clue to what the metal used to be. A wedding ring, electronic scrap, mine doré, and an old investment bar can all lose their recognizable forms when remelted. The finished bar does not display a picture of the mine, trader, workshop, or previous owner on its surface. The refinery has proved what the metal is. It has not yet proved what the bar is or whether the history attached to it can be trusted. Purity is only the first verdict. Human societies have struggled with that distinction for centuries. Gold's color made it desirable, but color alone never guaranteed value. Gold could be alloyed with cheaper metals. Weight could be manipulated. A dishonest mark could be struck onto an inferior object. A buyer in another city or country could not always melt every object and repeat the seller's assay. Trade required a method for transferring trust from an institution to the metal. In England, attempts to regulate precious metal standards date to the 13th century. Hallmarking at Goldsmiths Hall developed into a system connecting an article with independent testing and identifiable responsibility. The mark did not make the object pure. It told the next buyer that someone with authority had tested it and was willing to stand behind the result. In 1750, the Bank of England formally recognized refiners whose bars met the standards required for entry into the London market. This developed into the London Good Delivery List, now administered by the London Bullion Market Association. The system solved a practical problem. Large-scale gold trading becomes painfully slow if every participant distrusts every bar and repeats every destructive test. Standardization allows a qualified bar from an accepted refiner to move through the wholesale market with confidence. Confidence depends on continuing performance, monitoring, testing, and institutional reputation. Our newly cast bar must now face the second verdict. Is it authentic? The bar is weighed again. Its fineness and gross weight are used to calculate its fine gold content. Dimensions, surface quality, shape, and required markings are checked. A London Good Delivery Gold Bar is often called a 400-ounce bar, but it does not need to weigh exactly 400 troy ounces. The permitted fine gold content ranges from 350 to 430 fine troy ounces, approximately 9 to 13. 4 kilograms of fine gold. Its fineness must be at least 995. Smaller bars can be legitimate products in other markets without qualifying as London Good Delivery. A 1 kilogram 999. 9 bar may contain purer gold by proportion, yet still belong to an entirely different product category. The refiner's mark connects the bar with its maker. Fineness states the claimed proportion of gold. A serial or bar number links the physical object to production and assay records. Other information may be required according to the product and market. These marks create a new identity for the metal whose old identity disappeared in the furnace. But marks can be forged. A counterfeit bar may carry convincing dimensions, packaging, serial numbers, and a gold-plated surface. Simple counterfeit materials are often exposed immediately because their density, dimensions, conductivity, or magnetic behavior differs from gold. Tungsten creates a more interesting problem. Its density is close enough to gold that a tungsten insert can defeat a basic test based only on weight and size. That does not make tungsten invisible. Gold and tungsten transmit sound differently. An ultrasonic probe sends high-frequency sound through the bar and measures the returning signal. A foreign core, void, or internal inconsistency can produce a result that does not match solid gold. X-ray fluorescence can analyze surface composition. Conductivity testing, eddy current methods, density measurements, ultrasound, and other techniques add different layers of evidence. The appropriate combination depends on the product and suspected problem. Could a tungsten-filled bar fool someone relying only on color, dimensions, and weight? Yes, but a properly performed integrity test, such as ultrasound, is designed to expose the difference. The strongest bullion systems do not trust one visual impression, one number, or one machine. They build agreement between multiple forms of evidence. A bar can also fail without being counterfeit. Excessive porosity may interfere with ultrasonic inspection. An unacceptable surface, unclear marking, incorrect dimensions, or unexplained weight discrepancy can prevent a bar from entering its intended market. Some defects can be corrected. Others send the bar back to the furnace. The second verdict now arrives. The object has the required weight, fineness, physical quality, markings, and test results. It is authentic under the relevant standard. Yet even a genuine bar of pure gold cannot answer the question planted at the refinery door. Where did the gold come from? The laboratory can measure composition with extraordinary precision. It cannot examine a finished bar and automatically reconstruct every transaction that preceded it. Once different sources have been melted and refined, their old shapes no longer provide a visible history. Although specialized research has explored chemical and mineralogical fingerprinting, tracing refined gold back to a precise origin remains complex and cannot replace supply chain records. The past must survive the furnace as evidence. Process begins before the refinery accepts the material. The refinery identifies its counterparty, ownership, business activity, and relevant suppliers. It determines whether the incoming material is newly mined gold, recycled gold, a mining byproduct, or another permitted category. For mined gold, origin may involve the mine itself and the intermediaries moving material toward the refinery. For recycled gold, the relevant point of origin is defined differently, often beginning where the material returns to a refiner, recycler, or downstream processor. Recycled gold is essential to the market, but the word recycled is not a moral force field. If documentation is weak, newly mined or high-risk material could potentially be misrepresented as recycled. The refinery therefore assesses more than the metal. It examines locations, transportation routes, transaction patterns, supplier relationships, ownership structures, payment methods, and discrepancies between documents and physical deliveries. Material linked to conflict-affected or high-risk areas may require enhanced due diligence. Warning signs can include unexplained routes, sudden changes in volume, inconsistent declarations, attempts to hide ownership, or transactions that do not make commercial sense. The goal is not to label every miner in a high-risk region as guilty. Excluding entire communities without examining circumstances can push legitimate artisanal miners toward informal buyers and deepen the very risks responsible sourcing is meant to reduce. The harder task is to identify danger, improve formal access where possible, document the chain, mitigate problems that can be addressed, and refuse material when serious risks cannot be resolved. The Organization for Economic Cooperation and Development developed a 5-step due diligence framework for responsible mineral supply chains. The London Bullion Market Association requires refiners on its good delivery list to follow a responsible sourcing program and undergo independent assurance. These systems cannot guarantee that every historical fact about every atom of gold is known. They are risk-based systems, not certificates of moral perfection. That limitation is crucial. Calling gold responsibly sourced should mean that defined procedures were followed to identify, assess, manage, document, and report risk. It should not mean pretending that mining has no environmental footprint or that every human consequence can be erased by paperwork. The third verdict is therefore different from the first two. Purity can be expressed as a number. Authenticity can be tested against physical specifications. Provenance depends on a chain of evidence created by people and institutions before the original metal disappears. Now, the three verdicts can finally be placed beside one another. The first asks, is it pure? The second asks, is the finished bar authentic? The third asks, is its source sufficiently documented and acceptable under the applicable system? A bar may pass one and fail another. It can be chemically genuine but physically outside specification. It can be an impressive counterfeit carrying forged markings. It can be authentic gold while its sourcing documents remain insufficient. It can be a legitimate product in one market without qualifying for another. This is why a gold bar cannot be understood through its shine alone. Once the relevant assay, weight, physical inspection, markings, authentication, and sourcing requirements are complete, the bar can move into the next controlled stage of its life. It may be packed and transferred to a secure vault. It may be sold to a manufacturer, institution, dealer, or investor. In large bullion markets, ownership can change without the bar physically leaving storage. The metal remains on the shelf, while legal title moves between accounts. That quiet transfer hides the violence of the transformation required to create it. The finished bar does not show the drilling, blasting, and tons of rock moved to find its first particles. It does not show the crusher, mill, cyanide circuit, cathode product, or doré furnace. It does not reveal the chlorine, acid, electricity sampling, and repeated assay behind the number stamped on its surface. It also does not show a river contaminated with mercury generations earlier. Return to the scarred doré bar that entered the refinery. At the beginning, it carried value without certainty. Its gold content had not been proven. Its impurities remained mixed together. Its origin depended on documents that had to be checked. The refinery destroyed that bar so a purer one could take its place. Its old shape did not survive. The gold did. What carried the history forward was the seal, sample, assay, lot record, supplier documentation, chain of custody, risk assessment, serial number, and refiner willing to place its reputation on the result. A refinery, therefore, produces two things at once. It produces a gold bar, and it produces the evidence required to believe it. That is why pure and clean can never mean exactly the same thing. Purity belongs to chemistry. Clean sourcing is a claim about people, places, records, and responsibility. One can be measured inside the bar, the other must survive alongside it. Gold may be melted and reshaped long after everyone involved in its production is gone, and endurance is part of its power. It is also why the story attached to it matters. Fire can erase gold's old face. It cannot erase our responsibility to remember where it came from. If this journey changed what you see when you look at a gold bar, subscribe and share it with someone who has only ever seen the shine.